Professor Yuan, we can start now.
Okay. Okay. Very good afternoon, everyone. And it's the time for AP and AP Nexus for the live streaming. And we see you online again. And I'm Larry Yuan from Shenzhen and Zhejiang Lab. And today it is our great pleasure to have Professor Chu-Hong Kim from Pohang University of Science and Technology to give a review on the recent advances in photoacoustic imaging based on deep learning methods. And before his presentation, I'm going to spend a couple of minutes to give you some updates on the journals, AP and AP Nexus. As you have known, AP under the co-editor-in-chief of Professor Anatoly Zayas and myself, it has been already more than 5 years since its first issue. And you can see the summary of the recent published impact factor among the 98 JCR optics journals. We are ranked at top 3 together with Light Science and Applications. So this year we achieved 20.6 together. And we also have a new journal, or the sister journal of AP. It's called AP Nexus, which is also under the co-editor-in-chiefship of Professor Anatoly Zayas and Professor Weibiao Chen of Shanghai Institute of Optics and Fine Mechanics of CES. This journal is also a bi-monthly open access journal, and we received our index in the emerging SCI, which means next year, by the end of June, probably, we are going to receive our first impact factor. So we target the journal to be somewhere between 6 and 8, hopefully next year. And so, as I mentioned in the beginning, today we are going to have about 1 hour presentation by Professor Chu-Hong Kim from POSTECH, which is the full name is Pohang University of Science and Technology, in short, POSTECH. So Professor Kim holds many chair professorships from his university, and he's also the director of Medical Device Innovation Center, supported by Ministry of Education, and the vice director of POSTECH Caltech Biomedical Engineering. He is also the chief executive officer of a spin-off company to commercialize the preclinical and clinical photoacoustic imaging systems. He is a fellow of IEEE, SPIE, and Optica. He studied for his PhD and postdoc under Professor Li-Hong Wang at Washington University in St. Louis. Recently, he published a review paper on AP Nexus. As you can see from the screen, the topic is about recent advances in deep learning enhanced photoacoustic imaging. So I will leave the time to Professor Kim for his presentation. Please, Professor Kim.
All right, thank you, Professor Yun, for kind introductions. Maybe I need to share just a moment my presentation. So can you see my presentations?
Yeah.
All right. Great. So thank you for the invitation. It's my great honor to share our recent progress in this relatively new imaging modality called photoacoustic imaging. So we're certainly working on various aspects of this technology, from hardware development to the software development, including deep learning. So I'm going to share about our recent progress. also at the end of the presentation, we started our own company to commercialize it, to ensure our progress in commercialization. So my name is Chul-Hong Kim from Postech in South Korea. So my background during my master degree and PhD degree, we talk about biomedical optics, biophotonics, how light and tissue interact. As we all know, photonics revolutionized the biological studies. Many photonics people received the Nobel Prize in chemistry, in medicine, in physiology, even physics. Because looking at the tissue, which we cannot see with our naked eye, is very important to explore biological phenomena. So that's why optics is very important for biology and medicine. The problem, we use all optical methods for fundamental study in biology. Once we move to clinics, there are not many chances to use optical method. And people use MRI, X-ray, CT, and ultrasound in the positron emission tomographic imaging. So what is the problem? So as I said, during my master and PhD degree, we all know optical can provide in a very rich contrast, but the problem is penetration there. So because of the strong light scattering into the tissue. So we try to overcome, penetration depths of the pure optical imaging. At the same time, we want to provide, high spatial resolution. But using only optical method is difficult. So we combine light and sound together. So the technology name called the photoacoustic imaging. We use the phenomena called photoacoustic transduction from light to the sound. So motivation for this technology, we want to provide strong optical contrast, which is optical imaging, but we want to provide high spatial ultrasound spatial resolution, although in deep tissue. So if you look at the optical scattering in biological tissue, light scatters everywhere in the tissue. So one transport mean free path is roughly about 1 millimeter. So beyond 1 millimeter, light completely scatters, so you cannot get the good resolution. But in theory, light can penetrate tissue in deep region if you use near infrared light. Again, light scatters everywhere. Is very difficult to maintain the resolution. So in photoacoustic imaging, we combine light and sound together. In typical ultrasound imaging, we transmit the ultrasound, we receive the echo signal. In photoacoustic, we don't transmit the ultrasound, we send the optical light, typically in a pulse laser with a nanosecond with a safety limit. So, and then if you use a pulse laser, there is a light absorption and heat will be generated. So like this summer season, if you wear the black t-shirts, go outside, what happens? Your black t-shirts absorb a lot of light, your body temperature increase. It's basically same phenomena. There is a light absorption, there's a heating generated. So we are not talking about several degrees of the temperature rise. We are talking about millikelvin temperature, which is a very tiny temperature rise. Any elastic material, if they get hits, they start expanding. If there is a balloon, around the balloon, if you increase the temperature, balloon is expanding. So, since we use a pulse laser, there is a expanding and shrink that disturbing the medium, and then they generate acoustic signals. So 1 millikelvin temperature rise is equivalent to the 800 Pascal. That's very strong enough to be detected by conventional transducers. So there is an equation here in my presentation. This is the only equation I have here. We can see there's a pressure amplitude. Although we detect the ultrasound, the majority of the parameters here determined by optical property. So if you can look at from the last, it's called optical fluence. So F. So if we dump the more light, we can get strong signal. So that means we can eliminate strong light to the tissue. However, this F is controlled by safety limit. So we can use a maximum, but still under the safety limit. But this parameter is important, optical absorption parameter, coefficient. So everybody want to recover this parameter. Like our eyes basically distinguish these parameters on the surface. So mu A, optical absorption coefficient, is a wavelength dependent parameter, also concentration dependent parameter. For example, if you increase the concentration of a chromophore twice, optical absorption coefficient increases twice. Then, acoustic pressure increases twice. So we all know in optical people, we use, famous equation called Beer's law. Beer's law, in order to calculate attenuation of the optical signal, we can use the Beer's law. So in the Beer's law equation, between an input and output light intensity, there is exponential terms are there. But in this equation, this is not exponential relationship. This is a linear relationship. So increase the concentration twice, mu A increase twice, your pressure amplitude increase twice. Third parameter called heat conversion efficiency. So we all know any molecule excited by light from ground state to the excited state, they must release the energy. The one way to release the energy called the fluorescence. The other way to release the energy we call the non-radiative energy decay. That actually energy converted to heat. That's what we are detecting. There is a famous, FDA approved dye called indocyanine green, ICG. It's a green dye for human use. For green fluorescence, indocyanine green, ICG, when we excite this molecule with the light, almost about 10% energy converted to the fluorescence. That's why fluorescence quantum yield is about 10% in the water. But what about the rest of 90% the energy go? That actually energy converted to heat. That's what we can detect. So sigma heat conversion efficiency is basically 1 minus fluorescence quantum yield. The first parameter called Gruneisen coefficient, which is local temperature related. So it's not like in the global temperature, it's local temperature. So there is one technology in ultrasound called HIFU, high intensity focused ultrasound. It's widely used in clinic nowadays. So for that particular technology, they focus the ultrasound in one spot. They use that strong ultrasound for therapeutic purpose. Now that technology is extremely efficient because we can focus the energy to the one spot. However, since if highly focused ultrasound in one spot and the temperature significantly increase, somehow they need to monitor the temperature. The one technology using to monitor temperature, they use MR, called MR thermometry. But if you use a photoacoustic method with some resolution, we can provide the local temperature mapping. Then acoustic, and then propagate through the medium we detected by conventional ultrasound transducer. Luckily, once ultrasound generates during the propagation phase, ultrasound does not scatter that much. 2 to 3 orders of magnitude less scattered than light. And also ultrasound is extremely slow compared to the light. Speed of light is 3 times 10 to the 8 meter per second. Speed of sound only 1500 meter per second. So since ultrasound is extremely slow, we can get time resolved signal. But in optics, it's very difficult to get time resolved signal. That's why people use interferometric method. But in ultrasound, we can get time resolved signal to provide depth information. Then we can form 2D and 3D imaging is quickly. So what kind of contrast we can see? As you can see, we can use all kind of different color of the laser source, from UV light to the visible and the near infrared window 1 excitation source, or near infrared window 2. At each wavelength, we can image different molecules. So if you use a UV light, DNA and RNA absorb a lot of light. We can see cell nuclei without staining. And if you use a visible or near infrared window 1, hemoglobin absorbed a lot of light, so we can see blood vessel clearly without any inject contrast agent. Also, many people develop molecular agent in near infrared window 1, even near infrared window 2. So NIR near infrared window 2, we can image collagen and lipid. That's absorbed a lot of light. So what kind of information we can provide? Since we can see blood vessel clearly, we can provide, angiogenesis, which is related to disease. Also, we can see oxygen saturation. We can distinguish an artery and vein based on the color, or why color different between artery and vein because of the oxygen saturation. We can basically measure the oxygen saturation. We can see all kind of blood vessel structures. Also, we can see some molecular information, or we can see the blood flow. All these kind of things, photoacoustic can provide. So what we achieved over the last several years in POSTECH, using this technology, we developed super resolution for photoactivated atomic force microscope, or also near field scanning photoacoustic microscope. Well, we developed microscopy system, which is similar to the confocal microscope. We call ultra fast, ultra wide, label-free localized photoacoustic microscopy systems. Also, we develop intravascular catheter for endoscopy system combining photoacoustic ultrasound together. We have a whole body imaging system like a micro-PET, micro-MRI, micro-CT to image a whole body imaging system. So finally, we developed the clinical machine for human use. I used to work with the Philips when I worked with the Lee Hong at WashU. And then once I become an independent PI, I work with Alpinium Medical, Samsung Medicine in South Korea. About 5 years ago, we started our own company to commercialize these systems. Finally, I briefly introduce, pure ultrasound. This is not optics, but, the concept has been used in optics for many times. So we call the ultra-fast ultrasound to see the, nice structure of the tissue. So I'll try to introduce what we are doing at each imaging categories. The first one called optical resolution photoacoustic microscope. So these are the imaging modality like a confocal microscope, like a two-photon microscope has been used, biological and medical researches a lot. So if you look at, regular optical microscope, they use an objective lens to excite the tissue and detect the emitted beam through the objective lens, and they use dichrometer to, differentiate excitation beam and emitted beam. In photoacoustic, we need to use, excitation optical beam, and we need to use, ultrasound detector. So we cannot use dichrometer to distinguish in excitation and emission using regular dichrometer. So that's why we develop opto-ultrasound beam combiner. This is the device which is transparent to the optics, but reflected ultrasound, emitted ultrasound can be, through the dichroism between ultrasound and optics, and then we can detect in one position. So we call the opto-ultrasound beam combiner. So many groups in the world are using this kind of concept, to combine light and sound together. So using the system, we image the small animals like a mouse ear, mouse brain, mouse eyes, mouse thigh. So without any inject contrast agent, as I mentioned, the blood vessel absorbed a lot of light. We can provide, a very good vascular structure. The good thing, we don't need to inject contrast agent, particularly brain imaging. So we can see tiny blood vessel structure from the brain, which is good. Many people use two-photon microscope for the brain studying, but they need to, remove the scalp, which is the tissue, remove the skull. But in our case, although we remove the scalp, which is tissue, but the skull is intact. We don't need to remove any skull. So we directly image the, small animals of the brain blood vessels. So these are all 3D, so we can implement in 3D rendering software. So however, this system is commercialized by Microphotoacoustic in America, but about, I think it's 15 years ago, roughly. But still not many people using this technology in really biology research lab. So the issue, although we can provide a very nice image quality, the imaging speed is extremely limited. Sometimes it takes about 30 minutes to acquire this image. Sometimes it's 1 hour. So we need to expedite the imaging speed. So in particular case, we use some meters. In this case, we use the galvanometer. But this galvanometer working in the water environment, which is important because ultrasound heat propagate in the air. So, somehow, we need to make a water meter which works in the water environment. So it's what you call the water immersible meter. At the same time, this meter, need to scan light and sound together. So we develop the meter works in the water environment. Also, this reflect light and sound together in order to, expedite the imaging speed. So using this device, initially we image the small animals. So basically we monitor vasoconstriction induced acute hypoglycemia. Suddenly glucose level is increased in the blood vessels, and we want to see how the arterial structure is changing. So the number is showing here, 138 milligram per deciliter. That's the glucose level in the small animals. So we inject glucose solution directly in the bloodstream. You see the suddenly glucose level is increased. And then since we can segment each blood vessel, and then we can measure the diameters of the, these small animals' blood vessel. So this is the result. So black line show the change in glucose level. So initially, suddenly, glucose level is increased, and then it reached to steady states in maintain. That's why in the delta glucose level is suddenly increased and maintained. But if you look at the change in arterial diameter, once glucose level suddenly increase, as you can see, arterial diameter is maintained, and then it goes to steady state. So there is some vasoconstriction effect due to acute hyperglycemia. So these kind of things that we can quantify through the systems. Another technology, so previously I said we improved the imaging speed by making a water immersible scanner. So water immersible acoustic and optical scanner, previously we can provide about 100 frames per second along the cross-sectional imaging, 2D imaging, called B-mode imaging. Now in these particular papers, we improved the imaging speed about the 500 hertz. B-mode imaging speed, we can provide cross-section. So we can image vascular structure in the small animal's ear and the brain, and also vascular network in the eye. Since we improve the imaging speed so much, you can see we can directly see the flow information in microvasculature. Also, we can apply another new image reconstruction mechanism called localization. So localization of the fluorescence microscope achieve the super resolution imaging due to the fluorescence on and off process. So people receive the Nobel Prize. So in our cases, RBC can provide the strong photoacoustic contrast, so we don't need to inject, but we still can see on and off kind of concept in photoacoustic microscopy using RBC, which is completely label-free. But so that's why we see the on and off process, and then using that information, we improve the imaging speed. As you can see, these are conventional photoacoustic microscopy blood vessel imaging, but if you apply the localization imaging, we can even improve, spatial resolution more. So localization method, basically you acquire multiple images together and then you overlap each other. So although you can improve the spatial resolution, the problem is, you need to sacrifice temporal resolution because you need to overlap multiple images. So previously it took about 30 seconds to acquire 3D one localization imaging. So now we apply the deep learning acceleration method. So deep learning, we actually use ground truth images from fully localized image, but it takes longer. But if you apply the deep learning, we can save time. So that's why where deep learning method is working. So conventional localization takes about 30 seconds. If you apply the deep learning, it only takes 2.5 seconds. It's about 12 times improvement in imaging speed. All right, now we move to from small animal imaging to the human imaging. We monitor the perfusion process. So initially, we actually apply the cuff. So we block the blood flow. We measure the blood flow information in the human fingertip. This one is a cross-sectional B-mode imaging. You see the cross-sectional finger. So initially, we apply we block the blood flow. Not many blood vessels are coming. But, once you release the cuff, you can see new blood vessels are coming. So, there's a reperfusion process. Over the time, we can directly calculate the vessel density in the human blood vessel, and then these are related to microcirculation in the human. So these are all 3D data, so we can render in 3D with cuff and without cuff. Without cuff, we see new blood vessels are coming. So that's a human study. Also, by using two optical wavelengths, we can provide hemoglobin oxygen saturation. So here, red means higher oxygen, blue means lower oxygen. So basically, we block the blood flow in the human finger, and then initially you see a lot of red colors, which is higher oxygen. If you block the blood flow more, and then blood vessel become blue. So change oxygen saturation, it become decrease. Now we can improve the imaging field of view. Now we can see entire blood vessel of the human palm and forearm. Certainly we need to sacrifice the scanning time, but we can see entire blood vessel information in the palm and finger. So these types of application, people like it for security purpose. So now I want to move to another clinical application. So in the beginning, we can tune the optical wavelengths so we can see different colors of the molecule in the body. But in this case, instead of using, visible or near infrared light, we change the wavelengths to ultraviolet. So if you use ultraviolet, DNA and RNA absorb the light. So in the cell nuclei, there are full of DNA and RNA. So, we can look at the cell nuclei structure without any staining using this method. So in conventional histological, process. So during the surgery in operating room, surgeon takes small portion of tissue, let's say it's a brain cancer, and they actually send this small portion of the tissue to pathology department. Initially, they freeze and then they section and they stain using H&E, and then pathologists, they look at the tissue to show, details of the structures. But it takes about 15 to 20 minutes. But if you go to the pathology department, time is the issue. All these steps need to be done, very in quick manner. So, it's a laborious, it's time consuming. If you use our technology, we don't need to freeze, we don't need to section, we don't need to stain. We can directly look at the cell nuclei structures. So these are some examples we working on. So basically, we image the human colon cancer as ex vivo, but it's unprocessed tissue. We take that small portion of human colon cancer from patient, we just directly image it on our system. So top one is our photoacoustic microscope images. The bottom one is conventional H&E. As you can see, we can distinguish non-cancerous and boundary and cancerous area. So it's qualitatively, they're good because we can distinguish these two areas. But if you look at every single detail, conventional H&E imaging is much better than, our image quality. It's a resolution problem. This problem is coming from the hardware limitation. Now we applied all kind of deep learning technology. So deep learning technology, we can do three-step process. One is a virtual staining. The virtual staining means our image, initially it's a grayscale images. So, we converted our grayscale image to looks like in the conventional H&E. So these are our deep learning imaging result. It's very similar to the conventional ground truth H&E image. This is the first process. It's called virtual staining. This is a human liver cancer. So now second one, we segment the cell. Every single cell we segment. Using the deep learning technology, we measure the cell distance, cell area, cell countings. We apply the statistics. So once we have segmentation, our segmentation result is very similar to the conventional ground truth H&E imaging. So second, we successfully segment the cell structure. Last one, we applied again deep learning for classification, whether it's really cancerous tissue or non-cancerous tissue. So we can see the probability of the cancerous area. So basically, if we applied our deep learning technology, we can distinguish benign, malignant clearly using our images. Also, pathologists, based on the real H&E image, the image basically, accuracy is basically same. So we can do label-free histological image with the deep learning for virtual staining and segmentation and classification. So I can move on a little bit of technology development here. So in the beginning, in photoacoustic, we need to have excitation, laser excitation source, and then acoustic detector. So combining these two together in small form factor is difficult. So that's why we use opto-ultrasound beam combiner. It's kind of dichroic mirror, the special tools. But this kind of special tool is complicated. So in the end, we want to make a small size of the devices. Making small size devices using this in opto-ultrasound beam combiner is very complicated. So that's why, we brought a new idea called, conventional ultrasound transducer has the opaque color, so you cannot see through. But we developed new transducer called transparent ultrasound transducer. So this transparent transducer, as you can see in the picture, transducer itself is a transparent. It can work as an optical window. So we can illuminate light through this transparent transducer. So with high transmittance. Then, this is the first transparent ultrasound transducer we developed. And then we first, combine 4 imaging modality together called quadruple fusion imaging through the transparent ultrasound transducer for regular ultrasound, photoacoustic, optical coherence tomography, OCT, and fluorescence imaging. So as you can see here, this is the optical line for photoacoustic imaging. This is a regular ultrasound. This is OCT, for OCT excitation beam, and then fluorescence excitation beam goes through all same paths through the transparent ultrasound transducer. So we image the chemically injured small animal's eye. So before the injury, we can see normal blood vessels in the eyes. And then once we apply the chemicals, we can see new blood vessels are coming. So red one is all new blood vessels, cornea neovascularization. Using the OCT, we see the structural information of the cornea, thickness of the cornea that's related to inflammation. In ultrasound, we can see structure in deeper. And then fluorescence imaging, we apply the fluorescent dye and to see the inflammation area. So all 4 imaging modality can be done in one imaging platform. We can quantify something. This is early version of the transparent ultrasound transducer we published in PNAS in 2021. But at that time, the transducer is good for the transmission of the receiving of the ultrasound, but it has a weak transmission. So it's not 100%, 100% efficient. So recently we developed really highly sensitive transparent ultrasound transducer. The performance is very similar to, commercial ultrasound transducer, which has the color. So the issue, although piezoelectric materials are transparent, in ultrasound transducer, there is a matching layer at the front and the matching layer at the backing side also. All these need to be transparent. Also, we need to attach each layer using adhesive. Adhesive need to be transparent. Electrode need to be transparent. So finding all this transparent material and they efficiently attach each other, that's the difficult job. So we found proper matching layers, and then we developed newly formed transparent transducer with the performance is very similar to the commercial one. Now we can provide nice ultrasound imaging for deep tissue and nice photoacoustic imaging for the deep tissue. So previously we imaged on a shallow area. Now we can improve the imaging depth of 1.5 centimeter in microscopy. It's never happened before in photoacoustic imaging field. I can move on to more large scale. So far we see the micron scale resolution. It's like a microscopy. I want to move to the whole body imaging scanner, like micro CT, micro MRI, micro ultrasound. Conventionally, previous case, I use a single element transducer, fast mechanicals. Although imaging, the entire cost of the system is cheap, it some requires effort to image some area. Also, the field of view is limited. In this particular case, we are not using only single element transducer. We are using 1024 element transducer, which is, much more, 1000 times more number of transducer. Then, we can simultaneously acquire the signal. In this case, we need to have a multiple data acquisition system. In our case, we use a 256 channel data acquisition. In order to detect all 1024, we have a 421 MUX application. So we use a 20 Hertz laser. We can directly see whole body imaging. So these are structure of the whole body imaging from small animal. The color show the depth. So we put the animal in ventral, dorsal, and sagittal view. We can see, tiny structures, detailed structure. So we can see many main blood vessels from the surface. We see the liver, we see the spleen, we can see the spinal cord, the lips, even we can see the lung and the heart. In the below, we can see major organs. Also, we can monitor the dynamics of contrast agent injection. So this is before the injection of the ICG. So once you inject ICG, you can see signal is increase in the entire body. Basically, ICG go to the liver first, then go to the bloodstream. We can focus on one small area. This is the kidney area. This is the before injection. This is the real-time imaging. Now, ICG is flowing to the kidney and they accumulate there. And now the signal is bright. So signal from the kidney is bright, and the more ICG is accumulated, this triangle structure, which is the liver. So we segment only ICG signal. You can see ICG is flowing to the kidney, and you can see signal enhancement in the kidney and also in the liver. So we also image the brain. So red showed higher oxygen, blue showed the lower oxygen. So we did the oxygen challenge because we changed it, inhale the gas ratio. Initially, we provide, 90% of oxygen, which is in the red, and then we only provide 10% of oxygen. Which convert it to blue, and then we go back to the original, and then we convert it to red again. This is all real-time imaging. So also we apply the deep learning because in the beginning I said we have a 10,024 element. Our data acquisition for only 256. What we need to do, we need to afford to 1 mux, right? So basically our laser repetition rate is 20 hertz. In order to acquire all 1024, we need to have 4 laser shot. That's eventually imaging speed only 5 hertz. But if you use only 256, we can achieve 20 hertz imaging speed. However, image quality is poor because we use 1/4 of the element number. So we use deep learning between these two, and then we provide fast imaging, 20 hertz. We want to maintain the image qualities. Also, we use this imaging system for application, the cancer imaging. So we inoculate cancer cell in subcutaneous and under the skin, we monitor. Previously, all these biologists, without using this imaging system, they need to put a lot of, cancerous cells on small animal. They need to sacrifice every single day. But in our case, we can monitor the same animal for a long period of time because we don't need to inject anything. So basically, we monitor from 0 to day 11. We can calculate total hemoglobin, vessel density, and tortuosity within the tumor area. Also, we can render in 3D. These are all 3D results. We can render in 3D in whole body imaging scan with the other organs. We applied, we imaged it by using 2 optical wavelengths. We calculate hemoglobin oxygen saturation. Where blue dots are here is a lower oxygen. That's where tumor is. It's called tumor hypoxia. Then we inject the contrast agent called micelle form of IR780. So basically, it's accumulate more in the tumor area you can monitor. So these types of work, many people, routinely doing. But, we apply this one not for subcutaneous tumor. We apply this one for metastatic tumor. So metastatic tumor, naturally growing the tumor in the organ, not from the primary site to the metastasized site. So this is a day 0 to day 21. As you can see, time goes by. Initially, we don't see any tumors, in the liver area. As time goes by, you can see black dots with the blue color. That's where metastatic tumor is. So without any opening the body, we can image this. So blue means in low oxygen. So these are 3D rendered data with the metastatic tumor in small animals. And then we can inject contrast agent again, micelle form of the fluorescence dye. Pre-injection, we are now 100% where tumor is, but after injection of the, at 12-hour post-injection, we can see signals some accumulate here where tumor is. Finally, I can move on to the clinical machine. So you can see these types of clinical ultrasound machine in the hospital. I used to work with the Philips before, and then recently we started our machine is everywhere in the hospital. But unfortunately, we are not able to use a regular ultrasound. So they require some special ultrasound machine for photoacoustic and ultrasound imaging. So we put the portable laser system to image it in the clinic. In the beginning, we are very interested in the peripheral angiograph. Basically, we image the human foot. So at the early stage, we put the human foot in the water tank. At one scanning, we image only ultrasound. And later we fire the laser. So you can see grayscale imaging. Okay. So grayscale imaging is ultrasound. It's color show the photoacoustic. We merge them together. It takes about 20 seconds to acquire the images. This is the early one. So we see the ultrasound skin and the ultrasound bone information, and then we can see blood vessel information in tiny structures. So the main reason why we acquired the ultrasound first is we moved the system to the hospital. So mainly, diabetic patients, they actually, image, they have a lot of, blood vessel problems in their foot. So we moved the system in the hospital, but, we acquired the image for about 20 seconds. We asked them to, don't move over the 20 seconds, but it's many old people, although we said don't move, their foot is moving around. That's why once we acquire the ultrasound imaging, we provide the structural information. And then, a second scanning, we follow the contour of the human foot. And then, although they are moving around, we can get reliably, we can provide same quality of imaging. So ultrasound can image any part of the body. So previous on our foot scanner, now we develop handheld scanner. We image any part of the body, like a neck widely used. So one of example, we image the thyroid cancers. So thyroid cancer, ultrasound is gold standard. So they never miss the cancer, which means sensitivity is almost 100%. So medical doctor, they look at the grayscale imaging. If there is a thyroid nodule, they measure the size, they measure the shape of the nodule. And then, they give the number they call TIRAD score or ATA score. The different countries have different score, but it's similar. But, obviously benign, that's okay. Obviously malignant is okay. Always problem is in the middle. But medical doctor, once they suspicious, they said it's a malignant, which means they never miss the cancers. That's why sensitivity is 100%. But a lot of, then after that, they undergo the biopsy. After the biopsy, it turns out not the cancer. So that's why sensitivity high is specificity is really low. That's the problem cases here. In Asian country like China, Korea, biopsies are very cheap. So people just do biopsy, but in America, Western country, biopsy is expensive. So reducing biopsy basically save the money for the medical cost. So that's what we are doing. Using the ultrasound and photoacoustic, by adding photoacoustic information is there, we wanna maintain the high sensitivity, but we wanna improve the specificity. So here are results. ATA-P, so we made a new score called ATAP. ATA means American Thyroid Association score, that's based on the ultrasound, multiplied by photoacoustic probability. We make a new score called ATAP. If this number is above the 0.5, we suggest a fine needle aspiration biopsy. If it's below, we don't do anything. So we achieved about 100% sensitivity, but 55 specificity. So that's not low. If you use ultrasound itself, only 17% of specificity. But there is a company in America called Sino Medical. They recently achieved similar stuff. Not only thyroid cancer, they actually applied this one for breast. So breast and thyroid cancer, the phenomena is very similar. So we can apply this one to the breast cancer as well. Also, definitely we can image, cutaneous melanoma. Melanoma is typically pigmented. We can see the pigmented melanoma and the boundary clearly. And then we improve the imaging field of view. We call that panoramic imaging. We can see entire human arm. We can see entire human neck to provide detailed ultrasound and photoacoustic imaging. Final stuff I want to introduce called ultrasound, ultra-fast ultrasound Doppler, which is pure ultrasound, no optics is involved. But, regular ultrasound Doppler, it achieves about 80 frames per second. But high ultra-fast ultrasound Doppler, they can achieve on 1500 frames per second. If they improve the frame rate, typically they can see, tiny changes, which, regularly they cannot see. It's like, optical coherence tomography angiograph. no, OCT angiography, they use fast imaging speed and to see the tiny structure. That's the exactly same concept. So these are the red kidney imaging, B mode red kidney. You see the grayscale, you see the boundary of the kidney, but you don't see blood flow information there. But if you acquire these images so much at really, really fast imaging speed, what happens? You convert it to this grayscale imaging to the blood vessel imaging. Now you can see tiny blood vessel in that in vivo that's directly related to the flow information. So, this ultra-fast ultrasound imaging, they actually really achieve the super resolution imaging quality based on the high imaging speed. Finally, this is the imaging system we commercialize through our company. This is commercial ultrasound, clinical ultrasound. We put 2 wavelengths the laser. We have a handheld scanner. These are completely GPU-based programmable ultrasound imaging system and portable laser with a cheap price. So these are, because we undergo Korean FDA approval process, as you can see how the system is working. That's a clinical machine. There's some of one in Korea. I'm sorry about that. So the operator need to wear the goggle because, only thing we use a pulse laser, which is dangerous for eye. So it's a commercial system. In the screen, you can see, one is a grayscale imaging, one is a color, that's for photoacoustic. Previously, we use a water tank to image the, human foot. Now we don't need to use a water tank. So you see 2 types of imaging, gray and color. So we combine them together, we acquire multiple imaging over the time period, and then we can get, fine blood vessel information in 3D manner, and then we can provide 3D information. So this is undergoes Korean FDA approval process. We are going to move on to the real clinic. All right, that's what I prepared for today's presentation, and thank you for your attention.
Okay, thank you, Professor Kim, for the wonderful talk. And currently, we haven't received any questions from our audience.
All right.
So I think maybe they will submit some questions later. So I have a question
Yes.
about the histology application.
Yes.
You mentioned you use a MEMS technique. Is this MEMS same as the terminology MEMS?
Right.
So
Yes.
what is? I mean, I see you compared your technique with the frozen section
Right.
technique. So I have a couple of questions. Say in your case, do you need to slice the sample or you just use a thick?
So we use the thick. So
thick
because
sample.
yes, so basically it can provide depth information. So confocal microscope, regular microscope, it cannot provide depth, or otherwise they need to section, right? So these are automatically provide depth. So we can image it unsectioned. So without any cutting, we can image it also. Also,
so the vertical resolution is guaranteed by what? By confocal or by something?
It's called ultrasound frequency. So vertical resolution is actually determined by ultrasound frequency. That's the bandwidth of the transducer. So
that means you have a very broad band.
We need to use a broadband transducers. Yes.
Okay.
So all photoacoustic actual resolution determined by ultrasound bandwidth. So typically wide bandwidth transducer is a better for actual resolution.
Okay, so how big is the bandwidth?
So currently our transducer is around 40 to 50 megahertz, and the bandwidth is about it's a vary, but it's between 60 to 80%. Still our actual resolution is not very good. Like tens of micron, I think 20 to 30 micron at this time. So actual resolution is basically no good in our cases.
So that means you use a MEMS device as a ultrasound detector.
Right.
Is this the key point? I mean, you mentioned you can detect
MEMS is kind of, because we want to improve the imaging speed. So basically scanning is the problem, because regular MEMS, regular galvanometer, they are working in air, right? So because, in all optical method, they should working in the air environment.
Yeah.
But ultrasound does not propagate in the air. They should work in the water environment.
Yes.
So
Yeah.
we cannot put the regular MEMS, we cannot put the regular galvanometer in the water. No, because this is electrical devices. So, there is electrical problem. So we develop MEMS scanner, which is working in the water environment, inside the water, and then they scanning inside the water, they reflect and sound together. So it works as a sound reflector. Also, they work as the optical reflector.
Okay.
That's why we use the MEMS for high imaging speed.
So I'm just interested in two specs. One is the sensitivity of your MEMS. The other is the bandwidth. What can you give some?
So this MEMS scanner is not detector. This MEMS scanner only scanning. So it doesn't detect ultrasound. We use the regular transducer to detect. Only is moving, So this moving, we work as a meter. So imaging speed. So B-mode imaging speed. One cross-sectional imaging speed using our galvanometer, we can achieve a 500, this one directional scanning.
Okay, so this work is published on the which journal?
Yeah, we publish typically light science and application. Also, we publish laser photonics, some Nature Communication on these types of journal we publish.
Okay. Maybe I can find out more details later.
Right.
So let me see if the others. Oh,
by the way, I'm traveling to Shenzhen University next month.
Are you? So you are welcome to pay a visit to our campus.
There is a nanophotonics conference.
Nanophotonics.
Yeah, international conference on nanophotonics in optoelectronics and physics school, I think.
Okay.
Yeah.
There are a couple of questions from the audience. So great work, Professor Kim. How do you perform spectral unmixing?
Spectral mixing, yes. That's good question. So spectral mixing, because we use two optical wavelengths, and then we acquire two types of imaging, and then we distinguish two different colors. So mainly spectral mixing, ours is intensity based, but, at each wavelength, optical fluence in the tissue are different. So the very simplest way you can apply the Beer's law to compensate, fluence fluctuation by the tissue. Also, what we typically use, we basically acquire the local blood vessel signal along the depths. Using that, blood vessel signal, we can get kind of, exponential energy decay in the tissue of the optical fluence. We can estimate. So not just only Beer's law, using the local blood vessel information along the depths, we use that information we get the, compensated optical fluence map. And we use that one as the, spectral mixing. But certainly there is error. Spectral mixing is not perfect. It's a long-standing problem in this field. The only thing what we are doing, once we develop this spectral mixing method, we directly image the human. So we acquired the hemoglobin oxygen saturation from human artery and vein. We recorded the numbers, this number, at least, although there is error, we can provide consistent imaging result. So that's what we are doing.
Okay, thank you. There's another question. How does 1024 channel array perform compared to the 512 channel?
Right. So actually, initially we start from 1024 channels, but now we more moving on to 512 channels. So we actually have I didn't put any result here with the 512 channels, but image quality is very similar between 512 and 1024. So if you have more element is there, this is because this is based on the company who making this device, right? So 512, 24 channels are difficult to make. From the company point of view, you don't guarantee 100% all elements are alive. Sometimes elements are dead. That generate a lot of artifacts. But the company who work with us, they are happy to make a 512 element. So the image quality from 512 and 1024 is typically very similar. So, that's why we're moving to the 512 channels more instead of using 1024.
Okay, there's no other questions from the audience. So the last question also from my curiosity is,
Yes.
So in Korea, you commercialize the equipment for medical and clinic applications. So before you say send this to the clinics, do you need any organization to certify the product or the methods?
I think this is a very good question, though. So there is a two process. One is the Korean FDA we call the KFDA process. The other one in the hospital itself, they have an IRB committee. So our devices, if initially we need to apply IRB to the hospital. So few years ago, we sent our form to one hospital, and then what we need to do, why FDA process? FDA want to see the safety, right? If this machine is safe enough, we can do clinical study. So we consider this technology because we use a regular ultrasound. Laser is widely used in dermatology. It's already proven. So we call this machine is non-significant risk, called NSR device, non-significant risk device. So then, we send the application to the hospital. Then hospital need to determine, if they decide this is safe, we just do it in a clinical study without involvement of KFDA. It's a totally hospital they decide to do. If hospital IRB people, they're concerned about safety, they are asking us to move the system to the Korean FDA to get the safety confirmation, which is nightmare. You shouldn't do this. This one takes few years. Research lab never do this. It's a company can do, research lab never do this. So we apply the IRB to multiple hospitals in Korea. Some hospital, they agree this is a non-significant risk device. Some hospitals say they don't trust. You need to go to the FDA. So with that hospital, we don't do any clinical study. If hospital approve the IRB, we do clinical study. For all our commercial product, we need to go through KFDA, Korean FDA process. We need to prove safety first. Once we prove the safety, then we can go to the formal clinical study. It's like a phase 1 clinical, phase 2 clinical, phase 3 clinical. So proving safety, that's the key problem. So then you need to make a medical product. So medical product is completely different from the research product. So that's kind of these two process. I would say the IRB committee in the hospital, if they are listening to you carefully, they can approve. If they don't listen to you carefully, they just, go everything FDA process. So, communication with the hospital is very important here, I would say.
Yeah, not easy.
Yeah.
Okay, so it's 3:00. So we almost have a 1 hour
Right.
for live streaming. So I would like to conclude this 1 hour presentation, and on behalf of the organizer, China Laser Press, the AP Journal, and on behalf of our audience, I would like to thank you again for your wonderful talk, and hope to stay in touch. And you're welcome to visit China.
All right. All right. Thank you so much for invitation. I really be honored to be invited by this prestigious journal. I'm more open to any, collaboration, any not worldwide collaboration. I want to make a new friend. Thank you so much.
Thank you. Thank you. So thank you all online and everyone.
All right.
Okay. Bye-bye. Bye-bye.
Yeah.